So we're still in chapter 9 here. What we're going to talk about is something called hybrid orbital theory, to kind of add to VSEPR that we have kind of gone over the shapes and the polarity. So there are three different theories out there for how these molecules exist in three-dimensional space. One is called valence shell electron pair repulsion, which is, again, a big focus of chapter 9. But then we have hybrid orbital theory, and then a third is called molecular orbital theory, which I will talk about as well. So why do we need all of these different theories? Well, VSEPR does not conquer why do bonds formed in VSEPR theory. We just kind of put things together, pieces of a puzzle. But hybrid orbital theory kind of lends itself to a discussion of exactly how these molecules kind of organize themselves. So if I look at hybrid orbital theory, we are looking at sp, d, and f as what we call atomic orbitals. Okay, so that, according to quantum theory, is where we believe the electron exists about 90% of the time. Well, what hybrid orbital theory creates is something called a bonding orbital. So where you could actually have a sharing of electrons. And so these are going to have little letters associated with S and P to show what we call a bonding orbital. So let's start with our first example here of beryllium chloride. Okay, so if I look at beryllium, beryllium has, if I look at its S and P orbital, it's in the second energy level. I have 2 electrons in the 2s orbital, okay? But I know beryllium chloride exists, meaning I know that I can make 2 bonds there. So what I have here is there are no bonds to be formed at this point because this is all paired up. But if I were to take that electron and move it to the 2p, I now have what I call 2 locations for bonds to form. What I'm doing is those electrons are moving the furthest apart that they possibly can get, and then bond can happen. So if I think of it this way, if I have beryllium in the middle, I then put what I call a lobe where I could populate it with 1 electron. And then the chlorine can come by and share its 1 electron that's being shared from chlorine, and have what we call a hybrid orbital. So this is called an sp hybrid, because what has happened is I have blended the s orbital and the p orbital. I blended the s orbital and the p orbital. So remember, the s orbital, okay, the s orbital is more of a sphere. It's more of a sphere. And then a p orbital is more of a dumbbell shape. So when you hybridize these two, you're kind of what I call morphing them together. You've now created 2 lobes where you can make a bond. 2 lobes where you can make a bond. So it's called an sp hybrid. All you need to know is 2 locations means I make an sp. So you're involving the s and the p and making 2 lobes around it. So what about BF3? What about BF3? Well, again, boron has 2 electrons in the 2s and then 1 electron in the 2p. So it looks like I only have 1 location to form a bond, but I know boron fluoride, trifluoride, actually exists. So what happens is, again, thinking of it this way, we are going to take, move those electrons. So now I have 3 locations around that central atom, 3 locations around that central atom. So if I put boron in the middle and I put 3 lobes around it and put 1 electron in each one of those lobes, I then have a place for a bond to form. Okay, so this is the fluorines coming in with its 1 electron to then share and make a covalent bond. So I am taking an s orbital, okay, again a sphere, and I'm taking 2 of the p orbitals and making what I call 3 lobes around that central atom for an electron to go to, ready to make a bond. So that means I'm involving the S and 2 of the P, so it's called an sp2 hybrid. sp2 hybrid. All right, and then CH4, again, 2S, 2P. Hopefully you'll start to see the pattern here. I know that Ch4 methane, simplest carbon molecule, exists. I know it has 4 bonds. So the only way it could work is if I have 4 locations for those electrons to go. So I'm going to involve the S in all 3 of the P's. So draw a carbon in the middle, and then draw 4 lobes around it, okay, and populate it with 1 electron, okay? So then, excuse me for a second, hydrogen can come in and share its 1 electron, and we now have a bond, okay? So what is this called? This is called an sp3 hybrid. And again, it's going to involve 1 of the S, which is a sphere, and then all 3 of the P's. How this works is this is still a tetrahedral. So that is why we don't really teach hybrid orbital theory too much first year, just because it kind of complicates the situation. And it's still the same shape. Okay, this is still a trigonal planar. It's just this gives us more ammunition of why that bond forms. All right, so one additional thing before we conquer one other thing, and that is our friend ammonia. Now, ammonia has that lone pair on it. So how are we going to treat lone pairs in hybrid orbital theory? Well, in that lone pair, you have 2 electrons on that nitrogen, okay? So it has 3 bonds with hydrogen, okay? That's 3 locations for electrons to be between the nitrogen and the hydrogen. But you also have the lone pairs. So you got 1 lone pair on that central atom. That is also a location. So if that's the case, I have 4 locations around that central atom. So I have 4 locations around that central atom. 4 is always going to mean sp3. Okay, so I have to have a place for those electrons to live. So location is like a house, okay? And they talk about this in real estate, location, location, location. It's all about where your house is located. So these electrons as lone pairs need a place to live. So they need a hybrid orbital, okay? So if I involve an sp3, again, with a sphere and 3 of the p orbitals, I have 4 lobes around that central atom that I could have lone pairs living in, but I could also have bonds in there as well, okay? Now, where this gets a little crazy is where we go beyond the octet, okay? When I first started teaching, which wasn't that long ago, they used to think we had an sp3d and an sp3d2. And you will see in other practice materials sometimes on the AP website that they do include these beyond the octet. These have been disproven, okay? They used to think the d orbital started to get involved with hybrid orbital theory. Where hybrid orbital theory works the best is in organic chemistry. So I'll teach it sometimes in my advanced class because they do talk this way for organic carbon-based molecules. Where it falls apart is when you go beyond the octet, when you go beyond the octet. So if you have your sheet with all of your shapes, what we could do is next to each shape, just put the hybrid. And again, if you don't understand this whole theory, I'm just going to say that if you draw a molecule, I'm going to ask you to draw it, give me the shapes, both electron and molecular, and then tell me what the hybrid is. So if you can memorize the shape, you can memorize the hybrid. So linear is going to be an SP, trigonal planar is going to be an SP2, okay? Angular here is SP2, because again, the lone pair needs a place to live, so you have 3 locations. Tetrahedral is going to be an sp3. Okay, trigonal pyramidal is also an sp3. Okay, angular sp3, and then that's where it falls off. Okay, so once you get to 5, beyond the octet, you don't have any more hybrids. So again, if you just memorize that, you will be fine for hybrid orbital